Hi there. Welcome, everyone. We are so excited to see you for another installment of the WiSE Talks. The goal of this program is to be able to introduce you to some of the amazing women working in space exploration and help inspire you with some of their stories they're going to share. Just as a heads up, if you haven't been to one of these sessions before, we're really fortunate to have a scientist here with us. We're going to hear a really wonderful presentation for about 30 minutes, and then we'll have a question and answer session. We'll open it up. We want to hear from you. And in particular, if you're a young woman, we really want to hear your questions and answer them. So please feel free to put your questions forth in our chat, and you can give it the hashtag WISE if you're a young woman interested in science, and we'll make sure to get to your questions first. My name is Mimi Fuchs. I'm really excited to be hosting today's WISE Talk session with Dr. Kelly Lepo. I worked for years in telescope operations on Mauna Kea, and I love learning about space. So I'm really excited to be able to introduce you to astronomer Dr. Kelly Lepo. Dr. Lepo is an outreach and education scientist at the Space Telescope Science Institute, where she leads the development of outreach for the newly operational James Webb Space Telescope. She received her doctorate in astronomy and astrophysics in 2015 from the University of Toronto. Dr. Lepo has previously worked as a professor of physics at Gonzaga University, and she helped build the Large Hadron Collider at CERN. Today, she's going to be talking about the revolutionary mission of the Webb telescope. Before I hand it off to her, I just want to give a very big thank you to the Hawaii Science and Technology Museum for helping make this event possible, and for all of our friends at Microsoft who really helped start this WISE Talks program. So please, let's come together. Let's give a little virtual round of applause for Dr. Kelly Lepo. And I'll hand it off to her. And remember, if you have questions, feel free to post them in the chat as you think them. Dr. Lepo, I'll hand it over to you.
So thanks so much for that introduction, and thanks for having me. I'm always really happy to talk to students, and especially Hawaiian students. I did a lot of work during my PhD with the folks at the Canada-France-Hawaii Telescope, where I was the expert for doing outreach programs for everywhere that's not Hawaii, and I worked with people who did outreach in Hawaii. So it's always great to talk to students like you all. So I'm just going to share my screen real quick here. I think I'm here. Yes. Share. Okay, great. So today I'm going to talk a little bit about our infrared eyes on the universe, the James Webb Space Telescope. But first, I'd like to talk a little bit about my journey into astronomy. So just to start off, I'd like to, am I sharing the right screen?
Your screen looks good. We see a slide of how to become an astronomy professor.
Okay, great, good. Thank you. So how to become an astronomy professor. This is the normal path for how to become an astronomy professor. I just thought I'd put this out here first so that everyone knows sort of how one does this. And my path diverges from this a little bit, but let's first go through the standard path for how this is done. So you start off with an undergraduate degree, usually in physics, sometimes astronomy. There are some specialized astronomy programs, but a lot of people get their start as an undergraduate in physics. And then you go on to graduate school in the US. Generally, you apply directly to PhD programs. These take something like 4 to 7 years to complete. After that, you do a postdoctoral fellowship, usually 2 in astronomy nowadays. These are usually at a different university than from where you did your PhD work. So you end up moving a lot as an early career scientist. Then after that, you become an assistant professor, where you build up a portfolio to pass your tenure review. If you do that, you become an associate professor. If you don't, then you have to figure out something else, maybe a job at a different university. And then after that, some people apply to become a full professor if you're like a real big shot in your field. That comes with a little bit of a bump in pay and prestige. Not everyone does that until you hit retirement, at which point you can become an emeritus professor if you want. Usually you get desk space, and library access, but you don't have to come in every day because you're retired. Some people just, go retire to the beach. Both of those are valid career paths. So that's sort of the standard how to become an astronomy professor path. So now let's see what I did. So how did it start? I grew up here in Erie, Pennsylvania. I did my undergraduate degree in physics at the University of Chicago. When I was younger, I was interested in science. I was a bit of a nerd. I really liked science fiction, but also I liked other things. I really liked history and English and visual arts. And so I did the minimum number of classes I needed to get a physics degree, and then filled up the rest of my schedule with the history and philosophy of science and computer science and English classes, and fine art classes. And so that was really fun. I had a great time. Here is the University of Chicago's campus. It's very pretty, looking to downtown Chicago. While I was there, I did an undergraduate research project on the Quiet Telescope, which is a telescope that mapped the polarization of the cosmic microwave background, the afterglow of the Big Bang. What this is if you look at the sky with microwave eyes, you see this glow coming from everywhere, and that's the afterglow of the Big Bang. And if you look very carefully, you can see very small differences in the microwave light. And that tells us a little bit about what the very early universe was like after the Big Bang. So after that, after I finished my degree, I applied to grad school, and I didn't get in anywhere. So then I got a job because the professor I was working for had a friend who liked to hire students who had just completed their bachelor's degree to go work at technicians at CERN. Today, usually this is referred to as a post-bac, but I never heard anyone call me that while I was there. But I was working at CERN, which was this huge generational project to find the Higgs boson and understand very high energy physics. This was the view from my office looking over a vineyard to the mountains. It was very pretty. I was working on this, which was the ATLAS experiment. Here it is again, human for scale. And these blue things around the central hub here are the tile calorimeter. And that's the subsystem that I worked on. I'll show you a couple of photos that I took from when I was working down there to show you all the big electronic mess we were working with. Here's some technicians pulling out these electronics drawers and reconnecting the things. This is called commissioning, when we were putting the detectors together and making sure they all worked. And then we found out that they weren't quite working right. So we had to pull them out, replace some components, and put them back in. And so after I left, a couple of years later, they did manage to find the Higgs boson. And later that won the Nobel Prize. It was very exciting. And I had a very small part in making sure that the thing was not broken. So that was fun. After that, I applied to grad school again, and I did get in. I did my degree at the University of Toronto in astronomy and astrophysics in Canada. So here is another view of the campus looking to downtown, very pretty. Here's the view out of my window. It was nice. I could see Mississauga from there. What I studied was the type of stars that blow up as supernovas. They're called type 1a supernovas in the Magellanic Clouds. So here are the Magellanic Clouds. If you haven't seen them, that's okay. You can only see them from the southern hemisphere. They're little satellite galaxies of our own Milky Way galaxy. And I concentrated on the littlest guy down here on the lower left, the small Magellanic Cloud. And basically, my goal was to count the number of stars that could blow up as this particular type of supernova. And there are two thoughts for how this can happen. There is a white dwarf, which is the corpse of a star like our sun. After it runs out of fuel, you have this very hot, compact core. And sometimes these white dwarfs can pull enough gas off of a normal star companion that they get heavy enough and explode. The other scenario is that you have two white dwarfs that go around each other and then merge, they get too heavy and they explode. So there's a great debate over which one of these scenarios is the most likely to make a supernova. And so I decided to study this normal star and white dwarf channel to see if I could constrain or see which channel is the most likely to make a supernova. I like to liken this to wanting to know where babies come from. And so you have two routes to making a baby, maybe babies come from pregnant women and maybe babies come from storks. So one thing you could do is you could go and count all of the pregnant women in, say, Baltimore, and see if that matches up with the birth rate of babies. And if it does, then you can know that babies come from pregnant women. And if it doesn't, then maybe there are storks involved, right? So the punchline of my PhD thesis was that there aren't enough of this first type of objects, this white dwarf pulling gas off of a normal star, to match the rate of supernovas we expect in this small, dinky little galaxy, which means that the two white dwarf scenario must be the most dominant channel for making this, which means that maybe babies come from storks. Or, you know, maybe it's aliens blowing up stars for fun. Who can say? So after my PhD work, or during my PhD work, I really realized that I liked talking about astronomy, and I like teaching astronomy, and I like learning about astronomy, but I didn't really like doing astronomy research myself. So I tried to find a job where I could do all of the things that I liked and avoid the things that I didn't like. So I applied to lots of jobs over a couple of years, and I finally found a gig teaching physics at Gonzaga University. The downside to this was it was a one-year position, and generally in astronomy, you have to apply to jobs 1 year in advance. So basically, as soon as I got there, I had to start applying for jobs again. But it was a nice campus. I had fun. I got to work with some great students. And the basketball team there, if you've ever heard of Gonzaga, does really well. So I helped some students who were in the marching band deal with their physics classes. But after that year was up, I did get another job, and this time it was as the coordinator of the McGill Space Institute. So this is my office building. It was this old mansion, and my job there was to get astronomers and planetary scientists and astrobiologists and atmospheric scientists, all people who are working on like space-related things, to talk to each other and collaborate. And we'd hold seminars, and we'd have graduate student things, and it was a lot of fun. So I did that for about 3 years before I moved on to be the academic advisor in the physics department. But what I really wanted to do was to do outreach full time. So to talk to non-specialist audiences about space, because that was the most fun thing. And it took a while, but I managed to get a job at the Space Telescope Science Institute, where I work now. So here is a picture of my office building, although I'm at home right now. But STScI is the home of the science operations of the Hubble Space Telescope and the science and mission operations of the James Webb Space Telescope. And so there I get to work on stuff related to Webb, and I get to make sure all of the stuff that we put out is scientifically accurate. And I also get to do things like this, talk about the Webb telescope with non-scientists, which is a lot of fun. So I think this is a good transition point to stop talking about me and my journey and start talking about Webb and Webb's journey. But I'm always happy to answer any questions in the Q&A. So talking about Webb, let's start by talking a little bit about infrared light and exploring the universe with Webb, the science we can do, and a bit about the telescope itself. But let's start off with our last view of Webb here. This is an actual view of the telescope separating from the rocket fairing. So Webb was launched on December 25th, 2021 on Christmas Day. I was there with my family watching the live stream. It was very exciting. And here's our final view of Webb leaving the rocket and going off to its final destination, 1 million miles away from the sun. And we have this huge tennis court sized telescope that had to be folded up to fit inside of the rocket fairing. So we see it in its folded up shape here, and it has to go through a series of deployments to unfold everything very carefully. And in a moment here, we're going to see the first battery in it, but it couldn't continue on with its mission if its solar panel didn't deploy. And it was programmed to do so when it reached a certain angle with respect to the sun, or when it reached 30 minutes. And so it deployed earlier than we were expecting because it was at the right angle pretty quickly. And so we caught this moment on film. There it is. It's so cool, isn't it? Which was great. It was a really welcome surprise from Webb. So goodbye, Webb, and good luck. And I hope you do a whole bunch of really cool science. So here is Webb's unfolding sequence over the next month as Webb traveled from the Earth to its point L2, a million miles away from the sun. We saw this unfolding sequence happen, which started off with deploying and tensioning the sun shield, and then the secondary mirror came down in front. And then we see the wings of the primary mirror unfold. And once it's fully deployed, it starts cooling and we can start aligning the mirrors. So Webb orbits at this point called L2, the second Lagrange point, a million miles away from the sun. And it's there because Webb needs to be very cold. So it can't orbit around the Earth like Hubble does. It needs to be very far away from all of that heat. And you'll notice from this diagram that Webb doesn't actually orbit at L2, it orbits around L2 in this big orbit, which is actually wider than the orbit of the moon. And the special thing about this second Lagrange point is it's a point where the gravity from the Earth and the sun balance. So we can park our telescope here. It expends a little bit of fuel for station keeping, but not that much. So we have more than 20 years of fuel on Webb, which is great. That's like the one big consumable on Webb. And it orbits around with the Earth. So we always have the telescope traveling with us and sending back data. And it completes a full orbit around the sun, which means we can basically see all of space, all of the celestial sphere, if you will, except for the sun. Don't point your billion-dollar telescope at the sun. Very bad things happen. So why does Webb have to be so cold? It's because it's an infrared telescope. So you and me and the computer I'm talking into right now and the Earth are all glowing. We just can't see it with our eyes. They're glowing in infrared light. And Webb is a specialist in infrared light. It sees from sort of the red-orange side of the visible light spectrum, the color of Webb's mirrors, into the infrared. And you can see that there's a little bit of overlap here between Hubble and Webb's range. And the reason that Webb looks at infrared light is because a lot of things in the space are also glowing in infrared light. But also there's this problem of dust. Dust is everywhere in space. And by dust, I mean like dust, like soot or sand kind of dust. And so here we see a very famous image of the pillars of creation. And inside there, we can't really see much. It's blocked from our view. We have these cold, dusty columns where stars are forming and we can't see inside. Invisible light. If we look in the middle here, we have infrared light. This is a Hubble infrared view of the pillars of creation, and we can see through the dust. So we can see what's going on inside, and we can also see the background stars here. And then if we move to even longer and redder wavelengths, and my apologies for the lousy picture here, it will get better soon. We have the mid-infrared view of the same pillars, and we can see the dust itself glowing. So we can study dust, and we can also see through dust, depending exactly what wavelength you look at. So that's really exciting because dust is everywhere in space. But also, space is expanding. So as we look out into space, we look back into time because light takes time to travel. So if you want to see the very furthest things, if you want to see the very oldest things in the universe, you have to look at the furthest things in the universe. And as light travels, it gets stretched by the expansion of space. So things get stretched to redder and redder wavelengths the longer the light travels. which means if you have a galaxy that emits most of its light in visible and ultraviolet wavelengths, it gets stretched all the way into the infrared. So if we want to see the furthest things in space and the oldest things in space, we have to look with infrared eyes. Okay, so with that background, let's talk about a little bit of Webb science. So as I said, if we want to see the first galaxies, we have to look in infrared wavelengths. So here is a deep field, and by that I mean we're pointing the Hubble Space Telescope in an otherwise dark patch of sky for a long time, and we end up seeing all of these. I think all of these points are galaxies, which is wild, right? So we're seeing all of the history of the universe all smushed up on top of each other. And the one galaxy I'm highlighting here is our current record holder for farthest thing that we saw. It is a galaxy that's was formed about 400 million years after the Big Bang, or we're seeing it as it was 400 million years after the Big Bang. So that's 13.4 billion years in the past. This thing is crazy old, and you can see it's kind of red and lumpy and weird. And Webb will see much more of these. Webb will see some of the first galaxies to form after the Big Bang. We'll also see the history of galaxies over time. So we'll see the universe transition from these small red lumpy things into the spiral and elliptical galaxies we see today, and the history of galaxies merging together. And we'll have a unique perspective of this with Webb. We'll also study black holes, both near and far. So inside of our own Milky Way galaxy, there is a supermassive black hole called Sagittarius A star, but we can't really see it that well in visible light because of all of the dust that shrouds the center of the galaxy. But we'll be able to see through that with Webb to see the things that are orbiting around that black hole. Similarly, in nearby galaxies, we'll be able to see the gas and dust that's orbiting around their central black holes. And also we'll see the black holes and their jets and the interaction between that and stars and their galaxies to understand the relationship between black holes and star formation in galaxies. And looking to the distant past, to quasars, we have these supermassive black holes in these very distant galaxies, and we'll be able to observe those and understand the relationship between the first black holes and the first galaxies. We'll also understand the whole life cycle of stars from their birth in these cold, dusty, gassy nebulas, like this one shown here in both visible and infrared light, to normal stars, to the end of stars' lifetimes. Stars like our sun sort of cast off their outer layers gently into very pretty planetary nebulae, and more massive stars explode as supernovas. We can study all of that with Webb. One thing I'd like to point out is molecules. So molecules tend to wiggle and jiggle and vibrate and absorb light in infrared wavelengths. So if you want to study molecules in, say, star forming areas, the infrared is where you want to look, and Webb will be very good at that. But it's not just star forming areas, it's also planets. So Webb will be able to study planets in our own solar system from Mars outward. Again, don't point your several billion-dollar telescope at the sun because you'll fry it. But you can study everything else. We can study the atmospheres of Mars and Jupiter and Saturn and Uranus, and their moons and their seasons, and small things like comets and asteroid and Kuiper belt objects and all of that good stuff. We'll also be able to study planets around other stars. So here we have an image of 4 planets orbiting around a star. So the star is HR 8799, and there's a disk that's in front of the very bright star called a coronagraph, which is blocking our view of the star. So we can see these very faint planets orbiting around them. The planets are glowing in infrared light, and the contrast between the star and the planet happens to be biggest in infrared light. So Webb will be very good at observing planets, and Webb has a coronagraph, so it can make movies just like this. This movie is from the Keck Observatory. We'll also be able to understand atmospheres of planets. So if you have starlight that shines through a planet's atmosphere, we'll be able to detect the molecules inside of that atmosphere if you spread out the light into a spectrum. And so we'll be able to tell the composition of atmospheres of planets that are thousands of light years away. That's completely wild. You can do a little bit of that now, but Webb will be so much better at that So that's the science. Let's talk about the telescope. So I just like to emphasize that Webb is an absolute feat of engineering, and this engineering was made in order to reach these very lofty science goals. So the science drives the engineering. And some examples of things that had to be developed for Webb include specialized optics to align the mirrors, detectors that can capture and separate light from hundreds of different sources at once, and these really sophisticated thermal control systems, because if your telescope is too hot, it glows and all you see is the telescope itself. So it has to be very cold. Among the cool things that Webb will have are a series of different kinds of spectrographs where we can take light from an object in space and spread it out and learn about the composition and surface temperature and density and movement of objects in space. So lots of space telescopes have had spectrographs on them before, but Webb is really in its heart a spectroscopic instrument. Something like 70% of the time that astronomers asked for in the first year of Webb observations were all with spectra. So we're going to use this tool to learn about objects in space. It's pretty cool. And another piece of technology that had to be developed was Webb's mirrors. So the idea was to have Hubble-like resolution in the infrared. And it turns out that as you go to longer, redder wavelengths, you need bigger and bigger mirrors to get the same level of detail. So we had to figure out how to stick a 6.6 meter mirror into space when we only had a 5 meter diameter rocket fairing to put it on, which means we had to design a foldable segmented mirror. And another thing was the sun shield. So we have to keep this telescope very cold, and we don't want to use cryogenics like previous infrared telescopes because those run out after a while. So we're going to cool the telescope in a way where we don't have to worry about things running out, and that involves this sun shield design. So on the science side, where the mirror is and all of the instruments, it is something like 40 Kelvin, 40 degrees above absolute zero. So that's like minus 390 degrees Fahrenheit. But on the other side that faces the sun, it's very warm. It's something like 400 Kelvin or 260 degrees Fahrenheit. So that is a big swing in temperatures. And this allows us to have one side pointing away from the sun and doing all the cool science, and one side pointing towards the sun and the earth and sending us back data and being cool and all that. Okay. So one thing that I'd like to point out is that Webb is an international collaboration. It's might be billed as NASA's James Webb Space Telescope, but really it was an international collaboration from the start. More than 120 universities in North America and Europe helped build the telescope in 14 countries total. And here is a map showing the scientists that are going to use Webb in its first year. And basically, wherever there's a concentration of astronomers, there are people who are going to do Webb science. Pretty cool. Okay, so what has Webb been up to since launch? Let me start this video here. So it's been, after its deployments, it's starting to align its mirrors. So it has 18 mirrors, and in the beginning, each one of the 18 mirrors was acting as its own telescope. So this is the first images that Webb sent back, and we can see 18 spots here of one star. And if you wiggle each mirror a little bit in sequence, you can figure out which of these 18 spots belongs to which mirror. And you can even see the wings showing up here. And then we can take each one of these mirrors and we can move them into a hexagon shape so that we have each one of our spots in a hexagon pattern mimicking the mirror shape, because hexagons are the bestagons. And we can focus the mirrors a little bit. And then after that, we move the mirrors so that the spots all line up in the center. Like that. So that's an animation showing how it should go. here are actual images from Webb that it sent back. So these are the first images from Webb, but they're like, not the most, they're exciting to me, maybe not to you, but I think they're pretty cool. So here we have on the left side, the first is single point snowflake pattern stars will look like in the James Webb Space Telescope. So it will have very distinctive images. Pretty cool. Okay, and then what's next for Webb? We're right here in the middle of telescope. For that, we had all of those deployments. The telescope is still cooling. In a little bit, we'll be able to turn on the mid-infrared detector, which has to be the coldest. And then after that, we move into science instrument calibration, where we turn on all of the science instruments and make sure they work and get all the modes working. And then about 180 days after launch, we have the first images and spectra sent back, which is like July-ish. So expect a very big announcement this summer, highlighting some really cool images to showcase all of Webb's cool capabilities. I'm very excited for this. If you want to track Webb between now and then, there's a website. You can get to it from whereiswebb.com. And this is a screenshot from a couple days ago. It shows the temperature of the hot and the cold side of the telescope and exactly where they are in the testing process. Right now, they're in the middle of the aligning the mirrors part, and then they'll move on to the instrument calibration later. So I hope everyone is as excited as I am for the science that's going to start coming back in a couple months. We'll be able to capture the light from the first generation of galaxies in the early universe, help us map how galaxies change over time, study how stars form, live, and die, and explore distant worlds. And that's all I have. And I'm really happy to answer any questions.
Awesome. Thank you so much, Dr. Lepo. This was just such an exciting presentation. I got such chills when you showed those videos of the deployment of James Webb moving away and us being able to see these solar arrays unfold. It is just so exciting for us to be on the precipice of such discovery. So folks who are listening, if you have a question, this is your time to submit it. So please feel free to pass along any questions you have for Dr. Lepo, and we'll try to answer all of them as best we can. We also really want to prioritize our young women in science who are maybe interested in working in astronomy or physics or on telescopes or in space science technology in any capacity. So feel free to put the hashtag WiSE in your questions, and we'll make sure they go to the front of the queue. I have a couple questions because we get started and as the questions come in. Dr. Lepo, you talked to us about all these incredible science experiments and these science research topic areas that maybe we'll be able to advance significantly with some of the data from James Webb. How do you decide which scientists get to conduct experiments on James Webb? Are you just taking data and they get to look at it, or are you specifically taking data for certain scientist projects?
Yeah, so how it works is scientists apply for time. So anyone can do it anywhere in the world. You submit a telescope proposal, and STScI, where I work, coordinates all of this. And then it goes to peer reviewers, and we use a dual anonymous system. So you don't know who the astronomer is that's proposing, just their science. So it's all evaluated on the merits of the science, and then people get time on the telescope. In the first year, there's also a little bit of time that's given to the teams that helped build the telescope, and also the European astronomers who provided the rocket, which launched it into space. So those are like guaranteed time observations, but the bulk of the time on Webb is all allocated through who has the coolest science.
That is so exciting. And I imagine that at some point, as with other other observatories or other telescopes, at some point that data can become available to the public. Is that also true for Webb?
Yes, so there's a small proprietary period to make sure that the people who proposed for the science get to work on it first, but then it all goes into the MAST archive, which also is run by STScI, and anyone can use it. It's all in the public domain. And that's part of why the Hubble data has been so valuable, because there's this archive that allows you to search for data and gives you ideas about how to use it for science and all of that. So Webb will be using the same system, and we'll be able to have a legacy of all of this data for future generations.
That is so exciting. I remember in college, I did some research projects and we were able to just download the Hubble data, and Hubble gave us incredible riches of discovery. And I know that James Webb is going to do the same. We're starting to have some questions come in, so they might be a little all over the place, but I'll just ask them as they come in. The first question we have is, what got you interested in science and astronomy initially?
So when I was younger, there was a local branch of Penn State, and there was one astronomy professor there, and once a month there would be astronomy night. And so we'd go, and I remember being like real little and being scared that a black hole would eat me or something.
Yes.
And so ended up going so many times, and he only had so much material. So like I'd have like his talks memorized after going for a couple of years. And so that always had been an interest of mine. And then in high school, I realized I really liked the problem solving of physics. And so I went into my undergrad saying, I want to be an astrophysics major. And no way that that was actually going to happen, but I was just going to ride this out as long as I could. And here I am.
That is so exciting. So what advice would you give to other folks who are interested in science and maybe find themselves trying to figure out how to explore that interest? Advice for people who maybe want to grow up and become you and have a career trajectory similar to yours.
Yeah, so there's no one path into astronomy. So some people come into astronomy because they're big nerds like me, and they think that Star Trek is really cool and they want to do astronomy like that. And there's some people who really think that physics is cool and astronomy is the coolest way to apply that physics knowledge. But if you're a young person, I would encourage you to learn as much math as you can, because that ends up being important. And also computer programming is increasingly important. So the more programming you have under your belt when you start studying astronomy, the better prepared you'll be.
That is a great recommendation. Thank you so much for sharing that. I have a couple more questions about James Webb. You talked to us about how when you were earlier in your career, you had the opportunity to work as a technician on CERN, and you were able to be involved in these commissioning processes. And you mentioned that, sometimes things don't work as expected. You're able to go into the scientific instruments, pull some of the components out, close up, look at them, try to fix them, repair it, and put it back in. What do you do with a space telescope if you are not able to have a hands-on commissioning process?
Yeah, I mean, it's very different. And having this experience at CERN where if something broke, I could go like take a wrench and whack at it. You can't do that in space. So in space, you have to test things on the ground first. And that's part of why it's taken so long to get Webb into space. We have to make sure that everything works and we understand everything while it's on the ground, and we can mess with it before we launch it into space. But then there's also a lot of very talented technicians who can use everything we've learned about how Webb works on the ground and see how Webb works into space. And there's lots of backup plans in case something goes wrong. So far, it's all been going almost exactly to plan, which is completely banana crackers. Great. Not what I was expecting.
Yes, it was so exciting seeing those mirror alignment images and us seeing that simulation and then showing us the actual pictures we have. It is so exciting seeing it go through this very early calibration stage and seeing that things are going well. You mentioned a little bit in the beginning of your conversation about getting to do some astronomy in Hawaii. And I noticed that you used a couple of images from some of the telescopes on Mauna Kea. You showed us this really wonderful video of the Keck telescope taking pictures of these planets moving around a star. You showed us this beautiful picture, I think, of Jupiter that was taken from Gemini. Yep. And in that map of James Webb, I noticed that even though the islands are quite small, it looked like there were a lot of scientists there. Would you mind just speaking a little bit about what your experiences were working in astronomy on the islands?
Yeah, so I never got to go to Hawaii to do astronomy. Unfortunately, I studied the Magellanic Clouds, which are in the southern hemisphere, so I had to go to Chile and Australia. But if you are interested in infrared astronomy and you can't go to space, the next best place is Mauna Kea because water in the atmosphere, water wiggles and jiggles and it absorbs infrared light. So you want to be above as much of the atmosphere as you can be, and you need to be in a very dry place. And Mauna Kea is one of the best places in the entire world to do infrared astronomy. So if you see any infrared images that don't come from space, a lot of time they'll come from one of the observatories on Mauna Kea.
That is so cool. And I think, for folks who are watching at home who've had the experience of being able to go to Mauna Kea, you might recall as you get higher and up on the summit, the clouds are beneath you, right? We can even see without using telescopes how much further above a lot of this wetness we see that allows us to get these really clear, dry, pristine images, which is very exciting. Okay, so we have another couple of questions. We have one person at home who mentioned, "Thank you, Dr. Lepo. I really loved learning about the use of infrared light to help us further our understanding of space. I was curious, is there a way for us to do investigations with infrared light at home? I would love to try and see some of the things you discussed in person."
So that is a good question. Can I do infrared? Can I play around with infrared light at home?
Mm-hmm.
And to a certain extent, you can. So you can get little infrared cameras that can plug into your phone for a couple $100 last time I checked, that allows you to see the world with infrared eyes. A lot of home inspectors will use this to make sure that there's not heat or leaking out of buildings and that sort of thing. But if you want to do infrared astronomy, that gets very complicated. And so you need to have telescopes that are very cold and detectors that are very cold, and it gets expensive very quickly.
Yes, but I do. Oh,
another thing that's cool is a lot of television remotes will work on infrared light. And so you can try bouncing that off a mirror and see this invisible light controlling your television.
And I think actually our phones, like the average smartphone, the cameras, if you point it at a remote, you can take a picture of it. It's not something we can see with our eyes, but I believe with a lot of cell phone cameras, you can hold up one of these remotes and it has enough of a range that you often can see this little infrared light. We often do experiment at home for the remotes I have nearby, but I think that's one little experiment you might be able to do. Okay, a couple more questions. It was really wonderful to hear about some of the work that you did when you were a grad student and doing this research on the Magellanic Clouds. I've had the experience of being in the Southern Hemisphere only briefly, but it's incredible how beautiful they look. And it's so exciting to be able to study these little satellites of our galaxy. My question is like, you did a lot of this work looking at supernova. Are scientists going to be able to continue some of the work that you did using data from the James Webb? Is that possible that you would see a continuation of the product that you were working on in grad school with James Webb data?
Yeah, actually, I was just watching a seminar on the infrared sky, and one of the things that they were looking at was supernovas. So right after a supernova, it can actually get pretty dusty. And infrared light allows you to see through dust. So you can look at dusty supernovas right after they explode to try to figure out what caused them. And you can also look at other types of white dwarfs, which also are in the plane of the galaxy, and there's lots of dust in our galaxy, and you can't see them otherwise, but you can look at them with infrared light. So yes, you can do the type of research that I was doing with Webb.
That's so exciting. And there's a slight follow-up on that question. What science are you in particular most excited about that James Webb might be able to help us shed light on?
Oh gosh, that's a hard question. So one of the things that I'm really excited about is planets and atmospheres of planets around other stars, and to try to figure out what their atmospheres are like. Like, I want to know, are there other planets out there like the Earth or Venus or something like that?
Yes.
Are they like the planets in our solar system, or are they very different? And I'm also very curious about these first galaxies. What are they like? What generation of stars are in there? Are they the very first stars, or are they like the next generation after that? That sort of thing. Very interesting science questions.
I'm so excited. It really does just feel like we are in this golden age of astronomy where we finally have technology to catch up to so many of our ideas. And I really think we're going to have this treasure trove of data for generations to come that we can use from James Webb. I have a couple other questions for you that are a little bit more related to your career trajectory. You mentioned how when you went into college, you were excited by this idea of being an astrophysics student, and you weren't really necessarily sure how far you could go with it or what it might look like. But now that you've worked in this career and you've been able to experience quite a few different areas of it, from working as a technician on instrumentation, from working as a professor, for now being someone who gets to specialize in education and outreach. Maybe this is a little bit tough to answer, but I'd be really curious to hear you chat a little bit about how your expectations ended up, or how your reality of working as a career astronomer was a little different from your expectations as someone who was like a college student just interested in the studies.
Yeah. So, I mean, when you're a college student, the only people that you have as role models are your professors, right? So I'm going to go and become an astronomy professor because I want to do it in astronomy, and those are the astronomers that I know. And that's a very defined career path, and like I laid out in my talk. If you want to do something else, then that starts to get tricky. You have to figure it out your own way, which has been sort of challenging to build my career because I don't really have a set path to follow. But it's been fun and rewarding, and I get to do the type of things that I really like to do. So when I was the counselor who was working with physics students at McGill, I was helping them transition into grad school and try to figure out what they wanted to do. And, everyone wanted to be a pen and paper theorist because that's what it's like in your physics classes. So I want to be a cosmologist, and I want to do things like the problem sets I'm doing now. And I always tried to encourage them to expand their vision a little bit, to work on instrumentation projects, to figure out if that's the sort of thing that they like to do. Because it's sort of hard to envision a future if you don't have a role model or a career path in front of you.
Totally. I feel very fortunate that when I was in college, I got to do a project on Kit Peak, and I got to meet some of the scientists and technicians and operators who worked there. And up until that moment, I had never even considered that I could be working in observational astronomy at an observatory. I just had this idea that if you want to be an astronomer, you become an astronomy professor. And that was really a pivotal moment for me, seeing other people do this hands-on instrumentation and recognize that's something I can do. So thank you so much for talking a little bit about that. You mentioned also a little bit in your career that, maybe things went a little bit unexpected. You thought potentially you would go to grad school a little bit earlier. Were there other challenges that you encountered in your career that made you question if you wanted to be an astronomer? And if you weren't an astronomer, what do you think you would be doing?
The plan B, that's always a good question. So yeah, I guess I've always been sort of stubborn and just keep plowing forward, right? And so I've always decided that I'm just going to ride this wave as long as it will take me. But yeah, so I've thought about other careers that I've had, being like a freelance journalist writing about space, although there aren't a lot of those jobs either, or maybe a data scientist. That's sort of the path that a lot of astronomers who don't get jobs as professors end up doing. Although I wasn't completely very well suited for that because I didn't do a lot of big data work with my with the project I was working on for my PhD. So I'd have to learn more of that, but I could probably do it. I could figure it out. I'm confident in that. So yeah, I've encountered some challenges, but I guess I'm just very stubborn. So I've just been sort of plowing forward with what I want to do, and it's worked out so far, which is unusual, but great.
It is so cool to see you have a career working in space science and being able to do so many different things with it. I find that really inspiring, and I know that some of the people who are listening do as well. A little bit on that note, you mentioned how there's some people who go into data science. When you look back at the folks who you studied physics or astronomy with in undergrad or in grad school, what kinds of jobs do they have now? It's a little bit of a big question. Yeah.
Yeah, I know. So I think one person who was in my PhD class is still an astronomer other than me. He's working now on instrumentation and building balloon stuff. So some people have gone into teaching. Other people have gone into this data science route. Some people work for banks, or they work for Shopify, trying to, make it easier for me to buy stuff online, which I appreciate, that sort of thing. Yeah, so there've been, a whole different types of career paths. So if you think you're starting a undergraduate or even a graduate degree, thinking that you're going to be a professor, that's really the alternate career path. And everything else is what most people end up doing.
I think there's something that, maybe some people feel discouraged by that, but there's something that I find to be really exciting about this idea that astronomy can be a very versatile focus area for our graduate studies, for undergraduate studies. I think you mentioned this really, you put this very well in the fact that if you're working in astronomy, you likely are getting some hands-on experience working with electronics or instrumentation or optics. You get to have some experience coding. You get to have some experience with problem solving. These are all skill sets that can be widely applied to a lot of things. So folks who are listening, who are interested in doing astronomy, but maybe you're not sure exactly what you would do with it after, I hope you hear about some of these experiences and feel encouraged. There's a lot of things you can do with a physics and astronomy degree. Dr. Lepo gets to highlight it in her own career path, so many of those. But even outside of that, there's so many opportunities to apply the skill set you develop in astronomy and physics to a lot of different fields. And that's something I think is very exciting and really wonderful to get to hear. Folks who are listening, this is the time. We have a few more minutes for questions and answers. So if you have a question, feel free to submit it and we'll try to answer them as quickly as we can. Let's see if there's any others that we haven't hit yet. I am a little bit curious about where you see your future career. I hope it's okay to ask this. Do you see yourself still working primarily as an outreach and education scientist, or are there other things you're hoping to achieve in your career in the near future?
My plan for now is to continue working as an outreach scientist. This is a job that really suits all of the things that I enjoy doing. And so hopefully that Webb continues to work, so I will continue to have a job. That's the dream. Longer term, who knows? Maybe I'll end up, going and doing something else. I've, pivoted to different things throughout my career, and that's, been interesting to have new challenges. And one thing that I've found that after doing this PhD, I'm good at learning new things quickly. So I have confidence that wherever my career takes me, I will be able to pick it up and do it well.
That is so awesome. Let's see if we have anything else. I do have another question actually about James Webb. Oh,
sorry to interject. There's a couple of questions coming up in the Q&A. Can you see them?
Yes. Okay, perfect. Thank you so much for alerting me to those. Okay, we have a couple questions. Okay, so coming from an undergrad interested in astrophysics, what are some of the best ways to get involved with space technologies like James Webb? Are there opportunities for younger or aspiring astronomers that you think will arise with technology like the James Webb Space Telescope?
Sorry, could you repeat that question?
Yeah, so this is coming from someone who's an undergrad interested in astrophysics, and they want to know the best ways to get involved with really exciting space-based technology like James Webb. Are you aware of opportunities for younger or aspiring astronomers that will arise with this James Webb Space Telescope?
Yes, so there's a whole bunch of data that's going to start pouring in the next couple of months, and there's lots of internships that are available for college students. So things like there's a program at Space Telescope itself that allows you to do summer internships. And there's also REU programs across the United States that allow you to do that. And there's also ones in Canada that I was aware of. There's summer student programs that you can apply to, and some of them take, students who are not from the United States. So there'll be lots of opportunities to do research with Webb data coming up. And one of the cool things about undergraduate projects is that it's kind of okay if they are not successful. So sometimes professors will give you the like risky but cool projects to work on as an undergraduate. Like if you have a risky but cool project for your PhD thesis and it doesn't work out, then you're really screwed. But if it's just one summer, then, go for it.
That is awesome. And I think having this recommendation for REUs is really wonderful. So folks who are listening in, REU stands for the Research Experience for Undergraduates. If you Google REU Astronomy or REU Physics, you will find many dozens of experiences that are designed exclusively for college students who are interested in physics, in math, in astronomy. And often what you get to do is you get to go to a university or you get to go to another research laboratory of some sort, and you get to do a project for 2 or 3 months that summer. And it's a really wonderful way to get an idea of what parts of the research process you like, what you don't like. And as Dr. Lepo said, you know, it's a little bit less high stakes than finding yourself in grad school doing a research project. So definitely, if you're interested, look out for REUs, and it sounds like there'll be quite a few that'll end up using James Webb data, hopefully. Okay, we have another question. I'm not very good at math or computer science, but I love space science and problem solving. Are there other career routes in astronomy that I should be considering?
Yeah, so if you are not the I want to do physics problems all day type of person, there's also sort of more technical careers. There's lots of engineering that goes into astronomy, and some and some more technical hands-on things, like there has to be people who operate the telescopes and fix them when they break, or there's a cool Smarter Every Day that interviews the host's dad who worked on measuring the sun shield itself. So he was a technician whose job it was to measure the position of the sun shield as they messed around with it, which is cool. I suggest checking that out. At STScI, we also have people who are graphic designers and people who run the websites for us and people who manage the databases. So there's lots of science adjacent careers that aren't being a physicist.
Thank you so much for speaking on that. I think that is really important to remember. I'm pretty sure for the Mauna Kea observatories, actually, it's only something like 20 to 25% of the staff have PhDs in astronomy. As Dr. Lepo said, there's a lot of people who need to do engineering. We need people to do the communications. We need people to do the artistic visualizations. We need people to do our education and outreach. We need a lot of people who have an interest in problem solving in space science. So thank you so much for speaking about kind of the variety of opportunities we can find. We have gotten to the end of our session. Thank you so much, Dr. Lepo, for speaking with us today, for giving us such an exciting presentation about your career and about James Webb. And folks who are listening in, the fun doesn't stop here. We have another awesome session tomorrow. We would love you to join for our WiSE Talks. We're going to have Jenna Cadwallader with us. She's a flight technician from NASA JPL. She's a Jill of all trades who ended up attending a trade school for aviation maintenance and then landed her dream job building robots for space exploration. And so in her presentation, we'll find out a little bit more about how she worked her way up to become the primary drill bit technician for the NASA's Mars Perseverance rover. So thank you everyone who joined us today. Don't forget, you can register for tomorrow's talks online. The link is in the chat window, or you can go to specificspacecenter.com. Again, everyone, please help me come together, give a little virtual thank you, a big mahalo to Dr. Lepo for joining us today. Again, my name is Mimi Fuchs, and I will see you tomorrow for tomorrow's WiSE Talk session. Really looking forward to it. Mahalo, guys. Have a good one. A hui ho.
Mahalo. Thank you, Kelly.
Thank you.